Hello, I'm Frank Lamb with Automation Consulting, and this is the start of the ControlLogix Odyssey project. I'm going to start a project in RSLogix Studio 5000 version 30, and we're going to carry it through full development of the machine for many episodes, and I hope you enjoy it. Thank you. To start with, we're going to open Studio 5000. Again, this is version 30, and there are a variety of projects that I already have created here, and you can see those last projects here. They change the different 5000 presentations every year or so, come out with a new version. Again, we're on version 30 now, and this is the method that they do with this, but we're going to start a new project. In this case, I think we're going to start out with a 73 processor. It doesn't really matter in this case which processor we choose because we're going to use a simulator. The name of the processor is going to typically be the name of your machine, but in this case I'm just going to start the project with a project named PRJ1. This will be the name of the processor itself, so you might want to be careful when naming this. Call it something like line 2 or press or whatever the name of your machine is. You choose the size of the rack. We're going to just use a 7-slot rack here. That should be fine. I typically put the processor in slot 2, but a lot of people put it in slot 0. Again, doesn't really matter too much. You can see Studio 5000 kind of reopening here. This does take a lot of memory and it's not particularly fast. It's very powerful software, but it does suck up a lot of resources on your computer. The computer I'm using, this is Windows 10. It has, I believe, 8 or 16 gig of RAM, pretty good size hard drive. It's an i7 processor, but it's still not as fast as I would like it to be. Here we have the user interface for the program. You already have a main routine and a main program in a main task. We're not going to spend a lot of time talking about the particulars of Logix Designer in 5000. I'm going to assume you've already learned some of that in one of my videos or somebody else's classes. You can see here that in the I/O configuration there is already a processor. That's where we dictated it was going to be, and it's a 7-slot rack, so the first slot is slot 0, and then we have slot 1, 2, 3, 4, 5, and 6. I'm going to do some hardware configuration here, but we're going to be using an emulator, so I'm going to switch over partway through this project and start using the emulator and an HMI rather than using a real PLC. But we're going to do hardware configuration as if this was a real PLC. To add a new module, simply click on the backplane, choose the module you want. I'm going to put a couple of digital input modules here, and we'll use some nice diagnostic cards. The major revision, very important that you choose it here. You could choose version 2, but if you choose the wrong version and you have to change it, there is no way to change it by simply selecting this major revision and typing it in. You would have to delete the card. So very important that you choose the correct major revision to start with. This name is pretty much optional. You really don't need to name your input cards unless for your own documentation you want to know what they are. The Open Module Properties is clicked by default. That is going to open up the configuration of the card. The RPI is how often the processor accesses the input image table and updates it. 20 milliseconds is the default, and I almost always leave it right there. There are a lot of different things you can configure here. There are diagnostics for open wire. Unless you have extra resistors and things like that put in here, you do not want to click this because you would have to have a small trickle of current through whatever your input device is all the time, which would make it not work with push buttons, for instance. Change of state is primarily used for produce and consume tags and exchanging information with other PLCs. So it creates a change of state event and other PLCs can pick it up. And we're also going to get rid of the diagnostic latching here. Here are the different diagnostics. If you had set the latch diagnostics, this is where you would go and reset them. Once you hit either OK or apply, it creates the card. So there is our input card. Now we're going to put in an output card, more or less the same procedure. Everything associated with ControlLogix is 1756 bulletin. And the I's are inputs, the O's are outputs. They are all digital for OBs and IBs. OAs are generally AC, right? 74 volt to 265 volts AC. We're going to pick a fairly standard OB16. The diagnostics here, also the D, also means that it has electronic fusing already and some diagnostic capability for no load, things like that. So we're going to pick, once again, an OB16D. Same rule goes as far as the inputs. You want to choose your major revision properly here. Now I'm going to show you this minor revision. You can change at any time. If it doesn't happen to match whatever your physical card is, you can change it actually on the fly, online, or whatever. This compatible keying, this is present on all the cards also. If you say compatible keying, it means that the major revision must match, but the minor revision can be anything. The exact match means that both the major and the minor revisions must match exactly, or it will reject the card and not let you run. And this is often used in software validation in things like medical devices or anybody that uses software validation, pharmaceutical companies, that sort of thing. Once again, the name is optional. I can completely disable keying if I want to. Typically, I leave this at compatible keying unless I'm doing work for a software validated company. 20 milliseconds, again, this is how often it updates the card. We do use a producer consumer model in RSLogix 5000. This is a different method of updating I/O than typical scans use. Typical scans, you would just update the input and output tables at the beginning of the scan. So configuration, once again, lots of different things you can configure here. You can say when this card goes into program mode, do I want the output to remain on? Do I want it to turn off? Or do I want it to hold its last state? So there's a lot of configurability here. But of course they charge you a little extra for that configurability. The diagnostics, output verify. If your output gets disconnected, this would tell you that it's not there anymore when you are turning on the output. The no load is sending a small trickle through the output device at all times. And once again, diagnostic latching. Once you have diagnostic latching set, it will remain on even if the diagnostics heal themselves. And here is where you reset everything, including electronic fusing. I mentioned that diagnostic cards get electronic fusing automatically anyway. And you also have this nice pulse test that you can send a pulse through the output and verify that it's there. Oddly enough, when I have tested this, even if there's not a device there, I generally get the test says okay, even if there's not a physical device there. So I think really what it's doing is just checking that the pulse is present at the output pin itself. The backplane, this is really only showing things when you are online with a card, which we are not and we won't be. We're not going to be using real hardware here. I'm going to be using a simulator. I'm actually working in my house because of the recent tornado that tore apart my office. So that is the end of this card. Don't need to name it. I'll go ahead and change the revision just for fun here. It is something that you ideally would like to do. There's two of our cards here, input and output cards. We're going to put a couple analog cards in here real quick. There's lots of things you can set up for that also. 1756. The IF series is typically your regular analog outputs, and you can see that out here to the right. And we're going to pick maybe an IF 8. So that would be 8 analog inputs. Pretty standard card here. Non-isolated inputs, meaning they share the common. Again, naming it's optional. There is only revision 1, so you didn't have that selection. Make sure your revision matches if that's important to you. There are a lot of different ways to present your data. The floating data, a typical thing to do here is leave it in floating data and set it from, for instance, if it's a 0 to 10 volt card, go ahead and set it from 0 to 10 volts. Sometimes people like to use integer data. If you do that, your signal is going to be 0 to 32,767. One of the reasons that people do this is if you converted a project from something like a PLC 5 or a SLC 500, that is the way that your data would have come in, and rather than completely reprogramming everything, they'll simply leave that data at 0 to 32,767 and then scale it, which is what you would have done in a SLC or a PLC 5 anyway. Once again, not going to name the card. After I create the card, there are a lot of different things I can configure. The analog input cards do not update as fast typically as the digital cards do. So there's not a lot of advantage to reading the card all that often. It's going to already take a while to convert the signal, so you're going to have a little bit of a physical delay. Once again, module info only shows up if you're online with the card. Configuration, this is where you can scale the card. If I'm using a 0 to 10 volt signal, I want to make sure that I also change the low engineering unit. And you can see here, if I had 0 to 10 volts for the scaling for voltage, I would be getting at 5 volts, I would be getting 0. So I don't want to do that. And I want to make sure that this is also at 0. Real-time sampling. This is how fast you're going to physically pick up the inputs. Again, if you have a 0 to 10 volt signal, this is where you change it, and you can see it could be a 0 to 20 milliamp signal also. Sensor offset, you can put that in there. Digital filter, what this means is if there's a change, a very quick spike, this will ignore it. So you can put something in here like 1 millisecond, and a 1 millisecond severe change would not show up. Alarm configuration, you can set your alarms to different levels. You can drag them like this, right? And as soon as you drag it, it's going to go back to 0 here. And we'll kind of leave them where they're at. We'll go ahead and maybe put a high alarm at about 9 volts, 9.5 volts. So I can either drag this or I can simply type it in. We'll say okay here. You can do that for each one of these channels. You can physically calibrate your card, and we'll say okay. Digital filter time constant must be greater than twice the real-time sample period. Okay, we're going to drop that out then. Digital filter, we'll go ahead and put it in here. Low alarm must be greater than low alarm. Yes, that is true. Okay, probably shouldn't have done this because we're running out of time in this video. Go back into our alarm configuration, pull our low a little bit lower. Okay, there we go. Let's add a card. Output module. This will be an OF card. So we'll go down in alphabetical order. Standard OF8 card, that should be fine. We're not going to name it. Put it in slot 4. Pick a random revision, but ideally we would want to put our real revision in there. Module properties, RPI on outputs. We kind of do want it to be about as fast as possible, but you know, 20 milliseconds is probably fast enough. Lots of configuration. Once again, we can scale things. We'll go ahead and make it 0, 0, just like we did our other card. At least for this channel. I would have to set every channel. Once again, just like the digital output cards, I can set my channel if I go into program state or into fault mode to hold the last state, or maybe define it at 0 output. And there are various reasons to do this. This is not an alarm. This is similar to the alarm screen, but in this case, this makes sure that I cannot physically put out more than whatever voltage I put here. Right? So we're not going to set these. We're going to say OK. And we're going to end this video here. It's getting kind of long. So we will move on to configuring an Ethernet card in the next video. Thank you.